I can hope I can catch your attention for another half hour after this tornado. Ram, you mentioned this morning that you wanted to mobilize young people, an army of young people. What I'm trying to do is to mobilize an army of medical doctors. Because, you know, if you say you're a physicist, people don't listen to if you say I'm a medical doctor. So I'm hoping that this is something that catches attention also in the medical world. And yeah, we heard a lot about aerosols. They're very complex, the composition, etc. But in terms of air quality, there are some simplifications that have been made. Also to monitor, namely that the particles are being categorized in size bins. And the ones that are under legislation are the coarse ones, the big ones, PM10, and the fine ones in the middle, PM2.5. They have a size, diameter smaller than 2.5 microns. And the ones that are getting a lot of attention now, but are not under legislation, are ultra-fine. They're smaller than 100 nanometers. If you take it in terms of total mass, then you compare the same mass, then you'll find 64 fine particles in one coarse one, and 1 million or more particles in terms of the ultrafine. So they have very little mass. I will come back to them later. Also because the surface area per mass is not very much, of course, but if you look at this, the surface area per particle, but the surface area per mass is quite significant. It's much higher for the smaller particles. So, and they're most abundant. They actually can occur in urban environments in tens of thousands per cubic centimeter. And they contribute a large surface area that when you inhale it, it gets into contact with biological tissue. Now, there's a lot of work being done on air pollution and whatever, health effects. But something like this I could not find. So this is an image I created myself. This was not known. Or not known, it's known, but it is not being properly advertised, I think. The bigger particles, namely, when you inhale them, they're mostly soil and bioparticles like pollen or spores. They get stuck in the upper part of your respiratory tract. They sediment and they deposit up there. The very small ones, when they're being formed, smaller than 10 nanometers, they also deposit in the higher part of the respiratory tract because they are moved very quickly by Brownian motion. So these particles are not only affecting the upper part, they're also removed quickly. When you cough, you remove it, so throat clearing. The fine pollution particles in the middle, they actually reach deeper into the lungs. And I would say something like between 1 and 2.5 micrometers. They deposit by impaction and sedimentation. And they do not reach the deep part of your lungs, and they can also be removed because you have fluids in your lungs that is being moved upward by little hairs called cilia. So there's also a mechanism there to remove them. Not very efficient, by the way, so they can do a lot of harm anyway. But the very small ones, smaller than 1 micrometer, they reach very deeply into the lungs. They reach what they call the alveolar region. And they deposit mostly by diffusion. And also actually when you inhale air, much of it actually sticks in your lungs. So you can also exhale them. But the very small ones, actually 90% of them actually stay in your lungs. So the small ones are really the ones that are the biggest problem. And the small ones can actually also translocate from the lungs into the blood. I'll come back to this later. Now, the intermediate ones, the fine ones, they have the property that we heard about this today, that you can see them from space. They have a size that effectively interacts with sunlight. And so you can make these maps now at 1 kilometer resolution. For over 20 years we have such data. This is the data from the Van Donkelaar group. And you can see where the PM2.5 is highest. We can use these maps and then calculate that the global population weighted exposure is about 32 micrograms per cubic meter, which is more than 6 times more than the WHO guideline, which is now 5 micrograms. We can also see the hotspots here. We see We see East Asia, we see India, we see also the Sahara. The Sahara, of course, has a lot of particles, the other deserts too, but there's not too many people living there. So what we need to do is then normalize this also in terms of exposure. Now, the health impacts of air pollution, they come in two ways. When the air is very bad, we have short-term impacts like coughing and difficulty breathing, asthma attacks, etc. But what really matters most for health is the long-term impacts. It's simply chronic exposure causes chronic diseases. So you have oxidative stress in the lungs and the small ones also systemically, pulmonary systemic inflammation, vascular dysfunction, atherogenesis, which is plaque formation and impaired metabolism. These are typically the things that we knew about from smoking. So these are the sort of impacts that you would have now also from air pollution. The health outcomes for which there's really strong evidence now is ischemic heart disease, which leads to heart attacks, strokes, respiratory tract infections, which is particularly important for children, because a lot of children in this world, especially in the 3 billion poorest ones, still die from pneumonia because there's insufficient medical care. Then there's chronic obstructive pulmonary disease, COPD, asthma, lung cancer, type 2 diabetes. And the list is growing because there's much more evidence now also for decreased birth rate, premature birth, arterial hypertension, neurodegenerative diseases like Alzheimer. There is a list being published every few years in the Lancet that makes a ranking of health risk factors. And the orange ones are environmental ones, and you can see at the top particulate matter pollution. And this is DALYs, this is disability adjusted life years lost. So this is a percentage that is then attributed to this. And you see, this is still not very well known. I mean, everybody knows that high blood pressure is not good for you, and you go to the doctor and you get medication to do something about it. But air pollution is at least as important. Globally, smoking, etc., the list goes down. And Mark, if you allow, I will come back to this in terms of discussing particulate matter, clean air, compared to unsafe water. This was also mentioned by Kim. That is on place 13. And clean water is a sustainable development goal, and clean air is not. I think this is something we need to work on as a community. Now you can ask, how do we know all of this? How can we make such rankings? I can show you how we do that for air pollution. Is that you have hazard ratios that are being derived from epidemiological studies. We have for each 5-year category these curves, and here you see cerebrovascular disease leading to stroke for 5-year categories, in this case 60 to 64 years old, or ischemic heart disease, heart attacks also. And what you see here in these curves is that if the hazard ratio is 2, for example, when you are exposed to 100 micrograms, see if this works here, 100 micrograms, then the hazard ratio of ischemic heart disease is 2, which means that the likelihood of dying from this is increased by a factor of 2. So we collect all this information, and then we can actually make these calculations and also these rankings. I'm waiting for the next slide. Can somebody push a button from, there it is. So then we can calculate this number 7, Kim, I think it's now 7.8 million excess mortality. So this is mortality that would occur in a particular time of year, a particular time period in a year that would not occur in the absence of exposure. For the EU, this is about 320,000. For the United States, it's about 90,000 per year. Now, again, we see here East Asia, South Asia, also Europe, bad, but we, of course, have to realize that this is a combination of bad air and high density of people. So 55% of the global population lives in South and East Asia. So this is also a reason for these dense colors in these parts of the world. Again. There we are. So what we can do is we can normalize it, and we can calculate the mortality density from exposure to PM2.5 per 100,000 population. And now you see China and India are still bad, but you see also some countries in Eastern Europe sticking out pretty bad, and also in the Middle East. Now, what we can also do is we can use our model and then scale the concentrations that are being measured by these satellites by the amount of particles that are being removed. So when we remove fossil fuels, you see the picture looks completely different. We see still high numbers in Mongolia and the Middle East and in the Sahara regions, but in most other regions it is very much lower. So what this tells us is actually that everything related to fossil fuel use is causing this problem to a large degree. We can also calculate to what degree different disease categories contribute to these health outcomes. And here you see some very interesting differences when we compare the United States, for example, upper left here, and upper left here. You see a large fraction here, these blue and purple colors here also. This is Germany. This here is China also. But you see here in low-income countries, you see these brown colors popping up. And this is what I mentioned earlier, is that especially children suffer from air pollution. Their lungs are not full grown yet, and they're very sensitive. They get lower respiratory infections, and in many countries, this is a major cause of death for children. So we have the whole disease categories here. So because children die from air pollution, especially in Africa and other low-middle income countries, it also has a strong impact on the life expectancy in these countries, because if children die or the elderly die, this has, of course, a very different impact on life expectancy. If we plot this and compare with some other risk factors, such as smoking, by the way, this is only anthropogenic air pollution that I took here. So if we include natural air pollution like desert dust, which is of course difficult to control, this number would be even higher. But you see there is a lot of many areas where there is a lot of loss of life expectancy, and globally averaged, it's an epidemic of the same order of magnitude as tobacco smoking. If you compare it with parasitic and vector-borne diseases, which is mostly malaria, you see a global impact of 0.6 years. But again, of course, in Africa, this is a much higher number. And also HIV/AIDS, globally 0.7 years, also in particular Southern Africa. So this is consistent with what Kim just said, is that that there is a lot of life expectancy reduction from air pollution. Now I want to come to climate. I'll try to keep this short because most of what I wanted to say has already been said today. So we see an accelerating temperature increase in recent decades. The last 2 years, where one was above 1.5 and the other one's slightly below 1.5. 2026, because we have an El Nino coming up, I'm guessing, is going to be again above 1.5. So I think we are very close to 1.5 also from a statistical perspective. And in Europe, it's going even faster. And you see there's more variability because the area is smaller, but this is going quite fast, and it is interesting why it is accelerating. And of course, there can be many causes, but let me just discuss just one of them. This is also from the IPCC report, and this is another point I want to make, which has been made by previous speakers implicitly, but I would like to make it more explicit. If we look at carbon dioxide, you see this bar here is more than 2 watts per square meter. If you look at the total, it is between 2.5 and 3 watts per square meter. So for this reason, people just assume, okay, carbon dioxide is the main problem. It is a main problem, but it is not the main problem, because there are other problems as well, other gases that absorb long-wave radiation. And this is what Ram has discovered. They are at least half the problem compared to carbon dioxide. And then we have these aerosols cooling. So the net effect actually from CO2 and all the forces together looks quite similar. But it's very important to remember that there are many other forcers. But of course, we've heard that today, so I don't have to convince you. We've heard things about this too, so I don't want to go into this. But we have the direct effect, which in our model is about 0.3 degrees watts per square meter, and the cloud albedo effect is the biggest one, is about 1.1 or 1.2 watts per square meter forcing. The other ones are more difficult to quantify because they're implicit in the model and probably not very well represented, and they're very difficult to measure. What is relevant here is that we see these curves. It's going down. This is the aerosol optical depth, so this is the extinction of sunlight between the surface and the top of the atmosphere, measured both from satellite and from the surface. We see very consistent, this is now for Eastern and Middle Europe, a very consistent downward trend, which is coincident with an improvement in air quality, which is important, of course. This is now in Europe, this is going somewhere. This is Germany, and you can see since 2010, we have a population-weighted exposure to fine particulate pollution, which is more than halved. So something is happening, and it is going into the right direction. It's important to me to really say that this is a success. It's a success story. If you look at China, the air quality is still poor. But if you see where it came from, like 20 years ago, to me, what has been achieved is a success. And we can sell this as a success because this is mostly the consequence of getting out of coal burning and getting into renewables. So getting out of these fossil fuel burning energy production into renewables works. It works for air quality, and we can make it work for climate too. You can also see this from measurements of radiation at the surface done in Europe. And you see again, there's a lot of variability, and it's quite interesting. I don't have the time to go into this, but most of these peaks are actually in periods of heat waves and droughts, which are also accelerating in number. So the question whether this is a natural variability or climate change related thing is still open. But what you can see in these measurements that the amount of radiation at the surface, and quantitatively very consistent with what Ram has been predicting since INDOX, is increasing tremendously. About 20% is related to the direct aerosol effect by looking in clear scout scenes, and about 80% is related to cloud-related changes. And these authors estimate that about half of that is related to this indirect effect of aerosols on clouds. Ram, you don't like modeling, but this was a collaborative effort working with models. I just wanted to show this, the potential of releasing heat or increasing the anthropogenic signal. It's not so much because the aerosols are cooling the climate. They're really masking the greenhouse effect of the long-lived gases that's already there. I think this is an important perspective because in this view, if you remove fossil fuels, you have 0.5 degree more warming in terms of particulate matter. If you could, of course, this is unrealistic, but if you could remove all anthropogenic air pollution, you would gain 0.73 K according to this model. But the perspective here is that the 1.5 degrees are already there. Basically, the 2 degrees are already there. But we don't see it because the aerosols are masking it. And now we are successful in cleaning up the air, and now it comes out. And this is accelerating, or at least it contributes to accelerating the temperature increase. I don't know why I'm having trouble getting to... Yeah. So now I want to come to ultrafine particles. Actually, they're not relevant for climate because they're so small that the interaction of these small particles with light is not comparable to the ones with the fine particles, the larger ones. But there is a relation here to climate related to the sources. We have sources, then you have exposure, and then these particles, because they're so small, can directly get into your blood. They reach your alveoli, and then they can translocate into the bloodstream and affect other organs. And we work with colleagues at the Mainz University Medical Center that can actually show that when mice inhale microparticles, the problem is in the lungs. When the mice inhale nanoparticles, these ultrafines, the problems occur in the arteries, in the heart, in the brain. And the brain, there's another pathway because you have an olfactory bulb in your nose, and actually through there, they can directly get into your brain. So there are many pathways that these small particles can affect your health. And I want to go over this because I think this is going to become more of an issue. First of all, because we're very close to getting more legislation on this. Secondly, because the measurements are becoming more common in different countries. So why are they important? Because they dominate particle numbers. They're very numerous, especially in urban air. They govern the particle surface area that affects the tissue. They're direct combustion sources associated with all kinds of stuff, the black carbon that we heard about from Örjan and others. Also organics, which are very nasty actually, things like PAHs and quinones, that what Uli is working on with his group. So there's elevated exposure to these compounds with ultrafines. They have a large retention efficiency in the lungs. When you inhale them, they deposit in the alveolar region. They can translocate systemically and they can affect other organs. And yeah, this is a big map. One of the reasons why we had no handle on these ultrafine particles is because we did not have large-scale measurements. So there were some measurements by people who are interested in the processes, but not so much in relation to air quality. And so this is now can now be overcome by combining satellite data, I would say Earth observations, emission inventories, and the measurements that are available using machine learning. And now we can make these maps, and you can clearly see in background locations, the concentrations are rather low, of the order of 1,000 up to 2,000 or so per cubic centimeter. And in cities, you see high concentrations of them. And I have some other maps here. This is Europe, and here you can see, for example, in Southern Europe, like Milan, Barcelona, pretty bad. Eastern Europe, the concentrations of these particles are very high in the cities. Now, we have also done a meta-study using the epidemiological cohort studies to look at mortality. By the way, we always look at mortality, and we get the question often, why don't you look at disease progression, etc. That is because mortality data are the most reliable data we have. We know how many people die, what they die of globally. So that is why there is so much focus on mortality. And we can see here that especially in Eastern Europe, in the Balkan states, in Greece, the mortality density from these ultrafine particles is very large. Globally, we find about 2 million people die prematurely from these exposure. I've also mapped here the United States to have the nice message that the San Diego area looks worst of all. I find it amazing. Yeah, Los Angeles. Okay, that what I would have expected. Other cities look a bit better, but also like Vancouver, I would not have expected that. In Chicago. Anyway, we can also do the same trick for the United States, and you see the mortality density in California is highest of all states. This one down here that compares with California, this is the Monterey area in Mexico. Monterey area is like a 5 million people conglomerate of cities, which is extremely polluted. Okay, I'm sorry for the bad news, Ram. We can then use our models to attribute them to source categories. And here again, we end up with fossil fuel use. And that's why I think they are still relevant for climate, because we need to get rid of fossil fuels. And of course, this is a bit of a high density information plot, but let's take the world here. We see industry, domestic energy use, which is especially important in low-income countries, traffic and energy production using fossil fuels. You can see down there in the domestic part is more important, for example, in sub-Saharan Africa. And in high-income countries, the domestic part is small. It's mostly related to fossil fuels. So let me conclude from this, maybe some takeaway numbers, is that for PM2.5, the fine particulate exposure, the global excess mortality is 7.8 million per year, with some uncertainty. This is the 95 confidence interval. 63% is related to fossil fuel use. And actually, if you consider that there's 20% that we cannot do anything about, like desert dust or whatever, it is 80% of the avoidable mortality related to air pollution is caused by fossil fuel use. For the ultrafines, we find a global excess mortality of 2 million per year. 73% is related to fossil fuel use. So these are particles emitted in urban environments from burning that we do in our, of course, cars, but not only cars. And in high-income countries, this percentage is even higher. In Europe, we have 158,000 per year, 91% fossil fuel use. In the United States, about 90,000 per year, and about 93% fossil fuel use. So, nevertheless, I mean, I think we should sell air quality legislation as a success story, because if we always keep complaining and say nothing works, then you cannot interest politicians in doing anything more. But nevertheless, in spite of substantial improvements in air quality in some areas, and you can mention China, Europe, United States especially also, particulate air pollution remains to be a leading global health risk factor. Clean air is really crucial for human and planetary health, and it provides co-benefits for public well-being and long-term climate stability. And I'm mentioning here long-term climate stability because when we stop polluting the air with particles, then you can get rid of it quickly. And of course, this causes a temporary warming. But for long-term climate stability, there is really a co-benefit for getting out of fossil fuels and cleaning up the air. Replacing fossil fuels with clean alternatives is a really highly effective intervention to improve health, save lives, and also meet the United Nations goal of climate neutrality by 2050. And again, Mark, if you allow me to bring this up the day after tomorrow, clean air should be part of the Sustainable Development Goals. Thank you very much.